now we are going to see the introduction. So in introduction, we know that light, what is meant by light and what is the use of light. So the light, the very big source of light is the sun. So the sun emits the light. Light is also a form of energy, you know that. So without light we are not able to see the object. Because of the reflection of light we are able to see the object. So in 19th century, the scientists thought that optics and electromagnetics are two different branches. So optics and electromagnetics are two different branches. But later, James Clerk Maxwell explained that it's not a two different subjects, they are related one. So he explained that the different theoretical protection in the light of electromagnetic waves. So, and electromagnetic waves can travel with the velocity of light. That velocity of light means t into 10 to the power of 8 meter per second in free space. So electromagnetic waves starts from the gamma ray to that radio waves. You know that what are all the electromagnetic waves and what is the use of that waves. So in this lesson we are going to see that that one also. Okay. So that Michael Faraday. So scientist name is Michael Faraday. So scientist Faraday, he converts that he states the laws of electromagnetic induction. So using that we produce the electric field by changing the magnetic field. So electricity was produced by the law of Faraday's. So using the Faraday's law, now we are producing the electricity. In that, he changed the magnetic field into electric field. Then, that later after that Maxwell hits 1888, hits experimentally prove that electromagnetic waves. He demonstrated the experiment and proved the electromagnetic waves. So he showed that visually. That visually means he produced a spark on that ring, one closed ring. So from that he explained that electromagnetic waves and the properties of the electromagnetic waves. So using that property, nowadays we are using that laser, radar. Laser means you know the light amplification stimulated by emission of radiation. That technology. And another one is the radar, radio and detection and ranging. So these are all the very big inventions in the century. So nowadays we are using now we are in a digital world. So you know that 10th and 11th lesson we completed that. What is the digital world and how we are using that digital things in our day-to-day life. How we are using that cell phone, TV, mobile and communication systems and hospitals, and how we are using that X-rays. So using the X-rays, how we are diagnose the patients. Microwave oven. Microwave, you know that microwave is used for in the microwave oven. There are plenty of applications in the electromagnetic waves. So laser and radar is one of the examples for that. Okay. So here the displacement current and Maxwell correction to amperes circuital law. So it's one important thing that from the 4 lessons they are derived the different various equations. From that now we are going to see the displacement current and Maxwell correction. So already we calculated and we defined that current by using the Faraday's law. We produce the current and a small correction is made by the Maxwell in that equations. So that's called Maxwell did the correction in amperes law also. So now we are going to see the displacement current and Maxwell correction to amperes circuital law. So from the 4th lesson they derived that equation. See here, the closed integral of E vector dot dl vector equal to minus dou by dt of dou t of pi b equal to minus dou by dou t of pi b equal, instead of pi b we are writing here closed integral of s b dot ds, where E vector is the E vector is the electric field, B vector is the magnetic field. Okay. So here that electric field, when that magnetic field is changes, they are doing the differentiation, we can produce the electric field. So dou pi b by dou t equal to, it produces E dl. So we can convert that magnetic field into electric field. So these equations are indicating that electric field induced along a closed loop. That is electric field produced in one closed loop, that is indicating the closed integral. Here that it is an integral, so circle indicates that it's a closed integral. So E vector dot dl vector. So here we are going to integrate the value of electric field. So that integrated value of electric field is equal to the differentiation of the magnetic field, where pi b is the magnetic field. So by changing the magnetic field, you can produce the electric field, or we can integrate that electric field, you can produce the magnetic field. You know the integration and differentiation is opposite to each other. See here, electric field is induction along a closed loop is equal to the variation of magnetic flux with the time. That is equal to changing magnetic flux pi b in the region enclosed by the loop. So using that we can convert that equation, convert the one field into another field. So it was shown by this equation, and this was explained by that Faraday. So in this he explained that by changing that magnetic field you can produce the electric field. That was explained by the Faraday's. Then Maxwell came and explained that he thinking that reverse here, by changing that magnetic field we can produce the electric field. By changing that electric field we can produce a magnetic field. That was explained by that Maxwell. So here again you can see that the same equation in the reverse method. See here we are integrated the value of B vector dot dl vector. Here the B vector is a magnetic induction. So integrating the magnetic vector induction in a closed loop, you can get the pi e, where pi e is the electric field. So before Faraday explained that by changing the magnetic field you can produce the electric field. Here by varying the electric field, that magnetic field is produced. That was explained by the Maxwell. So the same equation is explained that opposite, so reversible. So here that magnetic field induced along a closed loop, that is equal to variation of electric field with the time. That is equal to changing electric flux pi e in the region enclosed by the loop. So we are considering a closed loop. So these derivations, that is integration and differentiation as occurs in the closed loop. We are integrating that value or differentiating that value. Here that one field is changes into another field. So electric field is changed into magnetic field will changes into electric field. So how that electric field is produced and magnetic field is produced, that was explained by the Maxwell. This is a small capacitor. Take the small capacitor, charging capacitor. See, this is a capacitor. So capacitor means it's a two parallel plate is here. So this is called a capacitor. That capacitor has the two electrodes. This is one electrode, this is another one electrode. One electrode is connected to the positive terminal of the battery. Then another one electrode is connected to the negative terminal of the battery. So when they switched on, that current is flowing through the from positive terminal to negative terminal, where that IC is called conventional current. So this is a conventional current. See in this circuit, here it is connected, physically it is connected, but there is a gap between the two plates. See here, there is no connection between these two plates. So this is called capacitor. But there is no connection, but that energy can transfer from one end to another. That is negative electrode to positive electrode. How that energy is transferred here? So here the flow of current is called conduction current, that is written as IC. Okay, right? So by applying that amperes circuit law, see amperes circuit law equal to integral of closed integral of B vector dot dl vector equal to mu naught into I. So here T is the time period. Depending on the time period, the flow of current is produced here. So closed integral of B vector dot dl vector equal to mu naught I into F. Suppose a closed, see when the current is flowing through the conductor, a magnetic field is associated with or it is surrounded by it. So here when current is flow from the positive terminal to that electrode, that is a conductor, that when the current is flowing through the conductor, that conductor is surrounded by the magnetic field. That closed surface area is taken as S1. So you can consider the point P is here, the P is located here. So the closed surface is called that magnetic field. It is associated with the conductor. So when the current flowing through the conductor, the magnetic field is associated or it is surrounded by it. So it's called the magnetic field. So when the magnetic field is flows like this, you can say that magnetic induction produced by the closed surface S1, B vector dot dl vector equal to, you can write that ampere circuit law, mu naught into IC, where mu naught is the permeability, here that IC is the conduction current. So that conduction current is there, IC is the conduction current. Suppose you are considering that closed loop, that closed surface area S2, it is not in a circular shape, it is like a hemisphere. So like this. So what will happen for that ampere circuit law? That ampere circuit law is become 0, because that circuit, that S2, the closed surface area, it is an imaginary surface. It is not a real surface. It is an imaginary surface. That imaginary surface is not contact with that any conductor. That conductor. So it is not contact with the conductor. There is an imaginary space is here. So there is no contact between the conductor and the sphere. So we take that equal to 0. The right side of the equation becomes 0, because there is no current is flowing in that closed area. Then, so how that current is flow from that positive terminal to negative terminal? Here, Maxwell explained that on one small correction. So it's called Maxwell correction. See here, it's an imaginary surface. It's a positive and it's a negative terminal. Then the current is flow from positive terminal to the positive electrode. It's called conventional current. So when the conventional current is given to that plate, here negative terminal is connected to the negative plate. There is a electric field is produced between the two electrodes. That means that magnetic field is converted into electric field. So electric field is produced between the two electrodes. So it stored that energy in the form of electric flux or the electric field between the plates. Then that field, the two plates are connected through that electric field or that electric flux. That current is flow from the positive terminal to the negative terminal. So this was explained by the Maxwell. So this is called a Maxwell correction. Current is flowing between the two electrodes. That electrode is called a displacement current. That's called displacement current. So that's why it's D is here. D is the distance between the two plates. ID is the displacement current. So according to that Gauss law equal to pi equal to Q by epsilon naught. So this is called Gauss law. So we will derive this equation in first lesson. So it's called Gauss law. So pi E equal to Q by epsilon naught. Or differentiating that electric field. So d pi E by dt, you will get dq by dt into 1 by epsilon naught. So the charge is differentiated here. So q is here. So dq by dt, that 1 by epsilon naught is a constant. So dq by dt, you can write that is a rate of change of charge is called flow of current. That current is taken as id, that is displacement current. So displacement current equal to that epsilon is brought into other side. So this is equal to id equal to epsilon naught d by E by dt. So you can get this equation. So here the displacement current can be defined as the current which comes into play in the region in which the electric field and the electric flux are changing with time. So here electric field or electric flux, any one of the quantity is changing between the two electrodes. So the changing the electric field and electric flux or electric field produces the current. That current is called displacement current. So now we can write that equation ampere circuit law like this. It's not 0 because it is conduction is here. So the electric field is conducted between the two plates. So here, so closed integral of B vector dot ds equal to mu naught I. This is called ampere circuit law. Instead of I, we can write IC plus ID, where IC is the conduction current, ID is the displacement current. So sum of the conduction current and displacement current equal to the flow of current, or the total current equal to the conduction current plus displacement current. Suppose that conduction current is become 0, we can write mu naught into ID. So it has only ID, that is displacement current. Suppose displacement current is become 0, you can write mu naught into IC. So IC only is available. So IC is equal to I, or when IC equal to 0, ID is equal to I. So sum of the two current equal to the total current I.